Okay, so we're going to keep going with ring theory, which we started on Monday. We're going to talk about ring homomorphisms, ideals, and other basic concepts of the theory. So basically a homomorphism is analogous to a group homomorphism, and an ideal is kind of like a subgroup. But things are a little bit different, and so we'll discuss how that is as we go along. But let me start with the definition. A map, well, let's put it this way. Let R and S be rings, and I'll just say from last time that I mean unital rings here. I'll let phi map R to S be a map. Okay. Just any map between the underlying sets. And then we say that phi is a homomorphism, or a ring homomorphism, but unless the context isn't clear, we would just say homomorphism if it respects the operations, right? So 1 phi of x plus y is phi of x plus phi of y. 2 phi of x, y is phi of x, phi of y, and 3 phi of y is 1. Right, so the first one says that it's a homomorphism of additive groups. The second one said that it respects the multiplication, and the third one says that it respects the unit. Okay. So in the book they call this a unital homomorphism, but in almost every normal context in ring theory, you would just call that a homomorphism. Every homomorphism is supposed to take 1 to 1. Okay, so all right, so that's a ring homomorphism. Let me give you a kind of a good sort of universal example, which is if R is a unital ring, there's always a ring homomorphism from Z to R. So the map from Z to R, which takes an element n to n times 1. And what is that? So that's 1 plus 1 plus 1 plus 1 if n is greater than 0, and minus 1 minus 1 minus 1 minus 1 if n less than 0. And take 0 to 0, of course. So this map, I'll say 0 if n equals 0. I'll give you all three. So this map is a ring homomorphism. Okay, so for people who are interested in this kind of abstract language, we say that Z is an initial object for rings. So in other words, it's initial, it's the first. In other words, it maps. It comes with a natural canonical map to every other ring that's out there. Okay, so I'll focus on that definition there. My camera's having a little bit of trouble focusing. See if I zoom it out there, that'll help. No, that is not helping. There we go. Okay, so that's the definition there. Okay, I'll upload these pages at some point, of course. Okay. So that's an important example of ring homomorphism. There are many more. I'm not going to get too deep into it now. We'll see them come up as we do more instances and examples. In particular, so Goodman jumps right into evaluation of polynomials. That's actually, you can actually do evaluation of functions more generally. So let me give an example, which is evaluation of functions, and then I'll give evaluation of polynomials. So example. So suppose we have R being a ring of functions. So let X be a set, F a field, probably like R or C, but it could be something else. So we have the ring, so let R be the set of maps. So the set of maps F from R, X to F. So this is a ring under the pointwise addition and multiplication. So this is a ring under F plus G. So F plus G of X is F of X plus G of X, and f times g of x is f of x times g of x, and 1 of x is the constant function 1. Okay, so if you take any field, probably the real numbers or the complex numbers, but it could be any, you can make a ring with and any old set in the world. So these could be maps from F to F. They could be maps from some other interesting set to F. Then you get a ring out of this situation by considering what this is called pointwise addition to multiplication, these formulas. And of course you can consider interesting subrings of this ring, like for instance, if F is the real numbers and X is some topological space, you could consider continuous functions. Okay, if you don't know what a topological space is, consider F is the real numbers and X is also the real numbers, or Rn, or some other familiar thing. Then you can consider functions which go from X to R, which are continuous functions or differentiable functions or smooth functions or something like that. Those are all subrings of this ring. Okay, so so this is where rings come up very naturally. And then what are natural ring homomorphisms in this context? They are evaluation maps. So let me move that over. Let's talk about evaluation maps. So in this setting, now let what's a good name? Alpha in F be any element. Okay, so that's fine. So there is a map from R to F, taking a function to f of alpha. So this map is called Eve alpha. So Eve stands for evaluated. So in other words, you take a function in your ring. Sorry. And I realize I've set things up wrong. Alpha in X be any element. Thank you. So there's a map from R to F, which takes an element of R, which is indeed a function from X to F, and evaluates it at the element alpha. It takes f of alpha, right, which lives inside F. And so the point is, this is a ring homomorphism. So this is a ring homomorphism. So let's check it. So Eve alpha f plus g is f plus g of alpha, which is f of alpha plus g of alpha, which is Eve alpha f plus Eve alpha g. So this is a very typical kind of proof that something's a ring homomorphism, by the way. So that's axiom 1. Axiom 2, Eve alpha fg is fg evaluated at alpha. That's f of alpha times g of alpha. Okay, so that's this. And then what is that? That's Eve alpha f times Eve alpha g. And finally, number 3, Eve alpha of 1 is 1 evaluated at alpha, which is of course 1. All right, so there's your ring. Those are your axioms for a ring homomorphism. Okay. So okay. So this is always true. This is a very general thing. And now we want to talk about how this works with polynomials. So sub-example polynomials. So sub-example of the example, which I'll just continue to call example. What if you have polynomials? So remember, we defined last time a ring Rx. So now so we're going to return to letting. Okay, so I used R a minute ago for this set of functions. So that's a bad, that might have been a little bit of a mistake. No, that's okay. Let's suppose now that S is a ring, and we have the polynomial ring Sx. So we defined it last time as a ring of formal polynomials in S. Right, so the elements of this ring are formal sums of the form, a0 plus a1x plus dot 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 plus anx to the n. It's completely completely formal thing. Okay, so now the point is that if S happens to be a field, okay, then I can get a map. So now let S be a field. So suppose S is a field, and let's call it F. So introducing S was kind of unnecessary, but I just wanted to recall that that existed in this generality. So then there's a map to R, which is the set of functions from F to F. Right? So the point is, a minute ago we introduced the ring, which was functions from any old set to F. So in particular, I could have functions from F to F. That's a very nice ring, not a field in general, but a ring. And now I'm saying there's a map from f of x to this set, okay? And what is this map? Any polynomial becomes a function. So now the claim is that any polynomial can be wrote as a function. So I take a naught plus a1x plus an x to the n, and what does that spit out? The function from f to f, which takes, so the function, so let's call this p of x, that's a polynomial, to f sub p, which takes alpha to a naught plus a1 alpha plus an alpha to the n. In other words, you can just make this thing into a function in the obvious way, and that gives a ring homomorphism from f of x to R. So in particular, I can evaluate a polynomial on any element by this formula, and that makes sense. Okay, so some of you are probably thinking this is a lot of extremely formal stuff. Aren't polynomials just a kind of function? And the answer is actually, unfortunately, no, not in general. So let me make a quick remark here. Which is, oh boy, apparently getting the pages apart is a difficult task. All right, so let me give another sort of example here on the tail end of this, which is kind of a reason why we have to consider this. So let's note the map from fx to R, which remember is functions from f to f, is not always one-to-one. Okay. So this is just some very counterintuitive thing. And so the example is you put f is z mod p. So we have an example of a field which is finite, right? And then the claim is that there are polynomials, there are two different polynomials that go to the same function. Okay, so why is this true? Well, in this field we have a lot of relations, right? So f minus 0 in this case is exactly z mod pz cross is a group of order p minus 1. It's actually cyclic, but that doesn't matter, right? So if I take alpha in f minus 0, then alpha to the p minus 1 is 1. Right? So that's a fact. We kind of mentioned this in passing before, but I'll say it very explicitly now. If I have a group of order p minus 1, every element's order divides. In fact, divides p minus 1. So in particular, I have a very simple relation, which is alpha to the p minus 1 is always 1. But that's a polynomial, right? So x to the p minus 1 minus 1 is the 0 polynomial. Goes to 0. Maps f to f under this map. Right? So this is a perfectly good polynomial of degree p minus 1. It's not 0, but the function that it creates a function, which is take any element and plug in this term, and that function is 0. So the map from fx to r isn't one-to-one. So fx to r isn't one-to-one. Right? 0 and x to the p minus 1 go to the same thing. And in fact, as you probably guessed, there are infinitely many things in the kind of kernel here. The map sends many things to the same thing. Okay, so that maybe seemed like a little bit of a digression there, but it's a bunch of examples of rings and ring homomorphisms that we hadn't seen before, so I think it was worth doing. Okay. All right. So let me give you actually the general version of this. So now let's finally call it lemma. General polynomial substitution. So I'm just going to give you specific examples. Let me give you the general polynomial substitutions. Let R, S, any rings. And suppose we have phi mapping R to S. Then a map R of X to S. Then, all right, I'm going to say it slightly differently. Then, for any S in S, there is a unique map phi prime from Rx to S such that phi prime of S, phi prime of X is S, and phi prime restricted to R is phi. So this symbol means restricted to. In other words, R lives inside Rx, right? Because you can take polynomials of degree 0. And so I can take phi prime and restrict it to the polynomials of degree 0, namely R itself, and then I can ask what map is that. And when I say unique map, I of course mean unique ring homom. Okay. So so this is the general polynomial substitution lemma. I'm not going to prove this because the proof is basically in the pudding, right? Like to state it is to prove it. In other words, phi prime of, I'll give, I'm saying I'm not going to prove it. I will prove it by just telling you what phi prime has to be. Phi prime of a0 plus a1x plus anx to the n is phi of a0 plus phi of a1 s plus phi of an s to the n. Okay, and if you think about it for a minute, that's it. That's the only thing it could possibly be in. So, so that's QE. And you have to verify that this is a ring homomorphism, but I'm not gonna do that. That's very straightforward exercise in unpacking the definitions. So this of course generalizes, saying there's a map from polynomials to any ring that does this. If the ring is R itself or F itself, or F as a field, as in the previous example, this kind of recovers the previous notes about evaluation. Okay, so this is the kind of general case of something that is easier in those specific cases, and the specific cases are what you often use, but this is very important. Okay, Goodman also goes on to give polynomials and several variables and all that stuff. I'm gonna not do that. Because it's a straightforward generalization, and we probably won't use it. And if we do, I'll just prove it when we use it. All right, good. So, yeah, very good. He also gives he also gives some nice applications to linear algebra, but we might do that. I might have our own section. If we had more time, I would have our own section on applications of ring theory to linear algebra. We probably won't, so I'll skip it. All right. So the next big topic is an ideal. Okay, so what is an ideal? Well, in particular, it's the kernel of a ring homomorphism. So let me give you the definition here. It's the analog of a subgroup in the ring theory context. But we don't have it is in particular a subgroup, but of course we have more structure. So you might kind of think that we should be thinking about just subrings. But in fact, we're gonna do a little bit better. So let me actually, before I define it, let me do motivation, because in fact we can kind of deduce what it should be from this. So let phi map R to S any ring homomorphism, and let I be the kernel of phi. Okay. So I is a subgroup. So 1 I is a subgroup under plus. It's an additive subgroup. Why? This is a map of groups, abelian groups, and so the kernel is a subgroup. Okay, no problem. 2. Let little I and I, R and R, any element. Then the claim is IR is in I, and RI is in I. So you have multiplication not just by another element of I, but by any element of the ring. And what's the proof? Since phi of IR is phi of I, phi of R is 0 times phi of R, 0. And that's phi of R, phi of I. Right? 0 times anything is 0 on either side. So, right? Boom. Right? So the point is that you actually are closed not only under multiplication by elements of I, which would be some kind of subring property, but by multiplication of any element in the ring. And that changes the game substantially and motivates the definition of an ideal. So definition, an ideal, a left ideal in R is a subgroup of R plus such that subgroup I of R plus such that R times I is in I for all R in R. And similarly, right ideal, you would be the same thing, but you would have I times R is in I for all R in R. And then two-sided ideal is what we defined above, both left and right. So I'll just say both left and right. Okay, so left, right, and two-sided ideals. All right, and the kernel of any ring homomorphism is a two-sided ideal. Left and right ideals are also very important. Remember, in many applications, perhaps most, the rings will be commutative, in which case it's the same. All three notions are the same. So, at this stage, I wouldn't worry too much about the difference between these notions, but just know that they're all out there. We just proved that the kernel of phi is a two-sided ideal. All right, so after this, we're going to construct, I guess, R mod I. Yeah, so Goodman proves a bunch of properties about simple ideals and all that. I think the most important thing to do with I, though, is to construct R mod I. Of course, Goodman also classifies ideals in Z and in KX. So let me do one example, which is classifying ideals in Z, and then we'll stop for the day, and we'll construct R mod I next time, I think, as well as do some other interesting things. So example, so what are the ideals necessarily two-sided in Z? So, well, in particular, ideals are additive subgroups. So they must be amongst, all additive subgroups are NZ. So all additive subgroups are NZ for N and Z. And I claim that they're all ideals. So claim all are ideals. So in other words, classifying the additive subgroups is the same as classifying the ideals. And what's the proof? Well, if M in Z, then M in Z is contained in NZ. That's it. And what's the proof? Well, it's clear, because this is N times something, and you're done. Okay, next time maybe we'll talk about ideals in KX. That's very, very interesting. We'll talk about the Euclidean algorithm, perhaps in a little more general context. Maybe we'll get to that in a bit, and we'll construct our mod I. Okay, so next time we'll construct quotient rings and do some other interesting things. I'll post this tonight, and I'll talk to you guys soon. There'll be one more homework. It'll go up later in the week, but there'll be a campus announcement about all that. So, all right, thanks for listening. I'll talk to you guys soon.